How science began editing cause and effect. It started with an outcome that arrived without a clear origin. An effect appeared, but its cause could not be pinned to a single moment. The sequence still existed, but it no longer flowed in a straight line. At first, this seemed like an analytical inconvenience rather than a fundamental problem. Science had encountered complex systems before. Feedback loops, delayed responses, nonlinear interactions. None of these were new. The assumption was that better resolution, deeper models, and more refined instruments would eventually restore clarity. Cause would be traced, effect would be explained, order would return. But this time, order did not return. To understand why this matters now, we need to revisit one of science's oldest assumptions. That causes come before effects. Push, then response. Action, then consequence. This temporal ordering underpins experiments, predictions, and accountability itself. It allows scientists to isolate variables, policymakers to assign responsibility, and societies to believe that outcomes can be controlled by intervening at the right point in the chain. That certainty began to weaken as systems grew more complex and more interconnected. In tightly coupled environments, actions echoed back on themselves almost instantly. Feedback loops blurred beginnings and endings. Effects reshaped causes before they fully formed. What once looked like a chain began behaving like a web, where pulling one strand altered the tension everywhere else. At first, this still looked like complexity rather than contradiction. Cause and effect were present, just tangled. Scientists believed the tangle could be undone, but then experiments revealed something more unsettling. By altering constraints around a system, boundaries, endpoints, or interpretive frameworks, researchers could change which causes mattered after the fact, without changing the events themselves. In quantum studies, later measurements influenced earlier probabilities. The events occurred in sequence, but their significance shifted based on how the system was ultimately observed. In adaptive systems, outcomes redefined which inputs were considered causal. The same data produced different causes, depending on how the system resolved. The timeline remained intact, but meaning flowed backward. This was not time travel. No information moved into the past, but relevance did. The system's endpoint acted like a filter, deciding which earlier paths were treated as causes and which were dismissed as noise. What mattered was not simply what happened, but what survived interpretation. Science had not broken causality. It had learned how to edit it. Once cause and effect could be reshaped by context, prediction changed character. Outcomes depended less on isolated actions and more on how systems interpreted those actions over time. Control shifted from intervening at moments to designing environments. Influence moved upstream, away from events and toward structure. As researchers explored this phenomenon further, causality revealed itself as conditional rather than absolute. Events did not automatically become causes. They competed for relevance within constraints set by the whole system. Some inputs mattered only because the system amplified them. Others vanished because nothing reinforced them. In complex experiments, change in the endpoint altered which intermediate steps mattered. A cause that seemed decisive in one configuration disappeared in another. Causation became emergent, shaped by feedback, thresholds, and interpretation rather than fixed sequence. This pattern surfaced across disciplines. In neuroscience, later decisions reshape how earlier stimuli were perceived and remembered. In economics, policy outcomes retroactively determine which market signals were labeled causal. In machine learning, final objectives decided which data patterns counted as meaningful inputs. The system, not the timeline, selected what mattered. The conflict emerged when prediction lost its anchor. If causes are not absolute, forecasting becomes fragile. Models built on linear assumptions failed in systems dominated by feedback. Explanation lagged behind outcome. Confidence eroded, not because science was wrong, but because it was incomplete. Researchers attempted to restore clarity by isolating variables more aggressively, but isolation itself altered systems. Removing context removed causality. What remained was artificial simplicity rather than truth. The tighter the control, the more distorted the relationships became. The emotional tension rose when scientists accepted an uncomfortable conclusion. Cause and effect are not just properties of events. They are properties of interpretation. The boundaries of a system decide what counts as a cause and what is dismissed as background. This did not make reality arbitrary. It made it contextual. Causes exist, but they are weighted by structure, not guaranteed by time alone. Meaning is not embedded solely in the past. It is shaped by how the future unfolds. Once science began editing cause and effect, it stopped asking what happened first. It began asking what made the difference. The conflict reached its peak when edited causality escaped the laboratory. In real systems, consequences arrived before clarity. Decisions had to be made without knowing which causes would later be judged responsible. In medicine, treatments changed which symptoms were considered causes of illness. In law, outcomes influenced which actions were blamed. In technology, final system behavior determined which design choices were label critical. Responsibility drifted backward after the fact, shaped by results rather than intent. This created a dangerous ambiguity. If causes are identified only after outcomes emerge, accountability becomes fluid. Success simplifies explanation. Failure complicates it. The same action can be praised or condemned depending on how the system resolves. Engineers recognize this clearly in adaptive systems. A design choice mattered only if the system amplified it. Many inputs vanished without trace. A few dominated because feedback elevated them. Causality became emergent rather than assigned. The emotional peak arrived with a realization that unsettled deeply held assumptions. Control no longer lived at the moment of action. It lived in the design of the system that interpreted actions later. This shifted power away from individual decisions and toward structural choices. Who sets constraints? Who defines goals? Who decides which outcomes matter? Responsibility moved upstream, long before any visible effect appeared. Once cause and effect are edited by context, freedom does not disappear, but responsibility moves upstream. And if structure shapes meaning, then the most important decisions happen long before any visible consequence appears. The resolution came with a reframing of causality itself. Science stopped treating cause and effect as a simple sequence and began treating them as a relationship shaped by context, feedback, and interpretation. This did not weaken responsibility. It relocated it. Attention shifted from isolated actions to system design, from individual moments to the frameworks that decide which moments matter. Researchers learned that editing cause and effect does not mean rewriting reality. It means acknowledging how interpretation, feedback, and constraints shape outcomes. Causes are not erased. They are weighted. This understanding reshaped accountability. In medicine, focus moved towards system-wide protocols rather than single errors. In technology, design decisions were examined for how they amplify or silence inputs. In policy, long-term structures mattered more than short-term actions. The deeper lesson was sobering. Power does not always announce itself at the moment of action. It often hides in the rules that decide how actions will be judged later. Science did not break causality. It revealed its architecture. And once that architecture is visible, ignorance is no longer an excuse. Designing systems means designing consequences, even when they appear far downstream. How science began editing cause and effect was not a loss of order. It was an invitation to take responsibility for frameworks that decide what order means.